should be using. Okay, so first of all, I want to thank you all for coming. I want to thank the King Faisal Foundation for inviting us, and thank you all for coming to this talk. So I'll be talking about recent progress in the study of the rental system and zero viscosity limit. So I am a mathematician. So I like writing equation, writing theorem and proofs. I know that I think many of you are not necessarily in the field of math, but more like in the field of science. So I'll try to not make it too boring for you, even though there should be some theorems. I will try to have like more or less three parts to the talk. Like I'll be showing you a few pictures that are, I mean, they translate more or less the ideas that we usually try to work on in fluid mechanics. Then I will be talking a little bit about applications. So there will be possible application in fluid mechanics, but there may be also application in other areas, not necessarily in fluid mechanics. And of course, there will be some math. Okay. So I usually like talking about like what are the important questions that we ask when studying the mathematical analysis of fluid mechanics. So here I'm more thinking about fluid mechanics, but from the mathematical point of view. So one of the important questions is the stability question. So stability of simple flows. These are fundamental questions that go back to the end of the 19th century, like whether simple flows are stable or not. There is a small general rule that if a flow is not stable, usually it's something that you will not see in nature. So for something to be seen in nature, it has to have some stability. Otherwise, if it is unstable, then you will not see it. So the next kind of question we are interested in is the long-time dynamic. So if you start with your system, then you want to understand what happens when t goes to infinity. That's also a very important question. Third question related to so-called transition between laminar and turbulent flows. So it turns out, like in physics, usually we have two kinds of theories. Like there is a laminar kind of theory where we are able really to describe precisely almost like each particle of the fluid, versus theories that trying to study turbulent flows. I mean, usually these are theories which are more ad hoc kind of theories where maybe people don't necessarily agree 100%. But it's very important to understand how the transition happens. So the transition is a part that we are still able to describe. I mean, when we arrive to turbulent flows, then usually we don't know necessarily precisely what's happening. Another question is related to the implicit limit. I think this is one of the major problems now with fluid mechanics, is to understand what happens when viscosity is taken small. Take Navier-Stokes, I mean, I write down the equations. Navier-Stokes is the model where we have viscosity in our model, but in many flows we are interested in, we can take the limit 0, then we need to understand what happens in this limit. And it turns out that this is one of the major open problems in fluid mechanics. It's true that we talk a lot about one of these millennium problems in math is the regularity for Navier-Stokes, where the solution of Navier-Stokes are regular or they can have singularities. This is but I think the problem of the implicit limit is maybe more interesting from application point of view. The talk will be more related to that actually. Another kind of question is the formation of singularity, how singularities form. We want to describe these singularities. And another question is the boundary layer. Boundary layer separation is also a type of singularity. I'll be talking a little bit about mostly the last 2 points, the implicit limit and boundary layer. So that will be the topic for today. Okay, so let me try to illustrate this question that I asked by pictures and then talk a little bit about related to some applications. So let's see here, for instance, we have the picture of a vortex. This is one particular kind of flow that we see a lot, like let's say hurricanes, or this is kind of thing that one can see. So, but then one can ask, since these are things that we see, it means that they have some sort of intrinsic stability into them. So recently there have been a lot of works trying to study the stability of vortices for the Euler dynamic. We are still not understanding everything, but there has been a lot of recent progress in this area. Of course, now these have important applications. I think few possible applications, weather prediction, also like in sandstorms. So I was thinking also about the region here, and I'll be talking a little bit afterwards about applications outside fluid mechanics. Another example similar to the idea of vortices is the so-called the red spot in Jupiter. This is also one instance of a huge vortex. It's a huge vortex on the surface of Jupiter. This has been there for a long time. And it's like a huge, maybe, we don't have a similar thing on Earth, but it is a huge flow that has been there for centuries, and it's there because it is stable. So the reason that it is there is because it is stable. So that should also give us ideas about how to study stabilities of these flows. Okay, people can read about it. It is, people who are interested in planets will find this really very interesting. Now, the third question I was mentioning is this question about transition between stability and turbulence. Here, let's say you start with a flow here that looks lamellar, so it's a nice flow, right? So that usually is we are able to describe, versus the flow here that became turbulent. So usually here we need more like averaging kind of models to describe this kind of what happened here. And this area is, so understanding how the transition happens is important to try to avoid it. Right? So there's a general rule that if you understand how an instability happens, and if you understand it very well, then you can find ways of preventing it. You can know what are the factors that can allow you to remove it or make it happen later. Yeah, unfortunately, this picture doesn't always show well. But this is kind of flow where we see how there are parts where the flow is laminar, but then it turns to turbulent, then it goes back to laminar, turbulent. So it's really a flow where we have areas where the flow is turbulent, but other areas where it is laminar. I mean, these are very difficult now to have even like theories to understand this, because like one has to be mixing different kinds of theories, and says that acceleration is the sum of forces. So here the acceleration is the first two terms represent the acceleration. This is the so-called material derivative. So even people who are doing physics, they know that material derivative, this is the partial derivative in time, but there is an extra term coming from transport. This is related to whether we are having a Laureate versus Lagrangian description. So this is the acceleration. These are pressure force, and then we have viscous force. Now this is a fundamental model of fluids, of viscous fluid, because of the viscosity term. Now the other fundamental model in fluid mechanics, which even was written earlier, like the Euler model, this goes back to the 18th century, whereas this is more like the 19th century. So the Euler model is the same, but without the viscous term. So we have the acceleration and the pressure force. Then the next equation in both is the incompressibility, is the first fact that your fluid is incompressible. So the density stays the same. There's no change in density. Now the main difference between the two equations, the other main difference besides this viscous term, is the boundary condition, right? So most of what I'm talking about is happening really at the boundary, right? And you saw it also in those pictures, is the fact that since here in Navier-Stokes we have a viscosity term, and this is from PDE, from partial differential equations, we know that when we have an equation with a Laplacian, so the important two terms, let's say, are these, so this is what we call the heat equation. So usually we are able to impose that the whole viscosity, the whole velocity vanishes. So again, maybe I didn't insist on the fact that mu is the velocity. So this is a vector, since I am in R2, so this is a vector in R2. So when I am doing Navier-Stokes, when I'm looking at Navier-Stokes, I can impose that the whole velocity vector vanish. However, when we do Euler, we don't have the viscosity term, so all we can impose is just that the normal part of the velocity vanish. Normal part of the velocity vanish means that the fluid can slip. Like the fluid cannot penetrate the boundary, but it can slip. Whereas here the fluid cannot slip. So, so this is a singular limit. This is one of singular limit, because when you try to pass to the limit, formally, like if one does a formal limit, he will say, okay, mu goes to 0, so then this term is negligible. Let me ignore it. Then if I ignore it, then this model becomes this one. Now, what I said is valid and can be justified if you don't have boundary limit from Navier-Stokes to Euler. What are the optimal conditions so that the limit holds? I mean, there are few results, but so there are results where we are able to say, yes, it works.
There are few instances where we are able to say no, it doesn't work, but these two are really still far away. So there is still a lot of room in the middle where we don't know. So that's why we say that the problem is still open, right? So we have particular examples where it works, particular examples where it doesn't work, but understanding in general, this limit is still a major open problem in fluids. Now, I would say the first main contribution in understanding this, and it is coming from Prentall, 1904. This was a talk at the International Congress of Mathematics in Heidelberg, and the idea that Prentall came with is the fact that there is the idea of boundary layer. So there is, even though we are trying to replace Navier-Stokes by Euler, but the viscosity effect will still be present in a very tiny boundary layer close to the boundary. So there's a tiny area close to the boundary where clearly we cannot neglect the viscosity, so we have to keep the viscosity. And to do that, he has to, we use the same word that what Martin was talking, to renormalize. So we have to introduce another change, another coordinate in the vertical direction. So here I'm writing everything we are doing this in a simple way, like in the half space. So my domain is the half space, right? So I'm just going to rescale the y variable so that I'm zooming on a very tiny area around the boundary. So when we zoom around that very tiny area, so that's how we introduce a new vertical variable, which is y divided by square root of eta. So that's my new variable. So now we take this sort of what we call ansatz. So you see here, I rescale this. I also rescale this viscosity, this part of the velocity, the vertical part of the velocity, I rescale it. And the reason we do this so that we keep the incompressibility condition. Okay, so we plug this in the Navier-Stokes, and then formally, that's what Prentall did. We derived the so-called Prentall model. Okay, so this model was discovered, was first introduced in 1904. It may seem slightly simpler at the beginning than Navier-Stokes because this is a scalar equation. So it's a scalar curve, whereas Navier-Stokes was a vector equation. However, this is a model that we call a non-local model. Non-local because the vertical component of the velocity, the way we recover the vertical component of the velocity is from the incompressibility condition. Okay, so at the end we end up with this equation. It has a term like the material kind of derivative. The material kind of derivative, the viscous term, and the pressure term. Okay, so since 1904, there were few results about this model, and they were mostly related to particular solutions, but the general theory in understanding this came really much later. So again, here, the way this model works is that one would like to take your half plane, so you want to approximate Navier-Stokes by two models. One, which is Euler in the bulk of your fluid, and another one in a very tiny area where you say, I'm going to describe it by the Prandtl system. Okay. Now, this is again the Prandtl system. I mean, one has to also couple it with some matching between the Prandtl and the Euler flow. The fact that when capital Y goes to infinity, this is in the Prandtl, you want to, so that is really matching the two models that you have. So you see like you are describing your flow by two models in two different regions. One region where you are saying Euler, another region you are saying it is Prandtl, but you need them to match when you need the matching between the two models. Okay. Okay, I have a long list of. Unfortunately, it doesn't show up. Okay. Yeah, I don't know. I think I should change this color. So, sometimes it comes well, sometimes no. So there is these are mostly recent papers about. I can mention these kind of works about solving in the monotone case. So if your flow is monotone, if the flow is monotone in the y variable, then there is a theory. Otherwise, one has to go to very high regularity spaces, like analytic spaces or Joffre spaces. Then we have results extending this to 3 dimensions. So usually, many of the results in fluids, we do them in 2 dimensions because it's simpler. But of course, like in real application, we need 3-dimensional models. So we always try to generalize the results to the 3-dimensional case. There are results, as I said, about long-time dynamic. And recently also now we understand slightly better the singularity formation for the Prandtl system. And it turns out that this is also related to the separation that I also mentioned. Now, what we mean by stability of Prandtl is whether we can really justify the fact that this Navier-Stokes model is well approximated by Prandtl. So as I said, till now we are still not able to give a complete satisfactory answer to this. Again, here what I mean by this, this is really a very, very partial kind of question. So normally what we want to prove rigorously that Navier-Stokes is approximated by Euler and Prandtl still vanishes when y equals 0. When y equals 0, u epsilon of y equals 0 is 0. Okay, I mean, I hope this was a simple kind of toy model, or at least for students who took ODE. If you are a student and you took ODE, you should be able to understand this, right? Now, if we go to Navier-Stokes, I mean, the logic actually is exactly the same. Like the logic about these two areas, an area where we have Euler, an area where we have Navier-Stokes, is exactly the same. The only difference that we don't have explicit solutions, so we have more complicated objects, like we have this Euler equation, and then it doesn't show. Okay, maybe I should not touch. I'll just tell you what is there. So we have Euler here. This is a boundary layer. So in a sense, this is my Euler flow. This is what we call boundary layer. So now this guy happens on a different scale, which is the y over epsilon. In a Navier-Stokes case, it's not over epsilon, but it's over square root of epsilon. That's the size. So then at the end we have this object usually is what solves the Prandtl. The Prandtl system this guy solves the Prandtl system. And this is the right scale. We have to rescale by square root of epsilon. Okay, maybe I'll take 5 minutes. Okay, so there were a few things I wanted to say. Okay, maybe I'll go fast on this. Yeah, I cannot do a talk without giving the theorem. So let me give a theorem. Yeah, so the theorem I'm presenting here is actually a recent result with Samir here about approximating. It's exactly about the question I was mentioning, which is approximating Navier-Stokes by Prandtl. I mean, taking a simple Euler flow, but allowing the Prandtl to be very general. All what we need is some monotonicity. Now, what is the enemy here? What can go wrong? I mean, and there are things that can go wrong, which is exactly again the picture I was mentioning here about possible boundary layer separation. So you see here in an area like this, you expect the flow to be well approximated by Euler and the Prandtl, but when you arrive here, you get boundary layer separation, and it will not be well approximated anymore. Again, when I talked about possible industrial applications, usually we want to make this happen later. Yeah, so now there are a lot of recent works also trying to understand precisely this separation point. I mean, I have a recent result about that, about describing that point. Okay. Okay. Yeah, I mean, these are results about the well-posedness for the Prandtl system, but let me mention two results that. So recently, this is a result I have with Nader where we described the boundary layer separation. So this was predicted by Goldstein in around 1945. So to describe precisely how the boundary layer separation can happen, the recent result I have with here is, this is a theorem that says that under some conditions, we can approximate Navier-Stokes by Prandtl. Okay, maybe I should not bother you more with this, but let me talk about applications. I mean, for me, like this kind of results, they have definitely important applications in weather forecast, in understanding sand dunes. But the most important kind of application now I'm thinking about are related to crowd dynamic, traffic flow. So it's true that the equations are different. I mean, some people think about crowd as an intelligent fluid. So meaning that, but in both cases we have interaction between different. I mean, we are thinking now of people as particles, and there are interactions. But we have a lot of models recently that are used, for instance, in I mean, for traffic it has been there for a while. For crowd, it's more recent that we have models. I mean, there are ideas of transport, diffusion, interaction, which are present in both cases. So, of course, I mean, we have a lot of possible applications, for instance, in power or things like that, where there have been models, and I'm trying to understand how we can apply some of these ideas to these crowd dynamic equations. Of course, it's very important to keep in mind that a lot of advances in science happen with the idea of analogy. So we saw it also in the talk of Martin, where you have same kind of ideas, but apply to different kind of questions which are really seem unrelated. So what's the relation between finance and the other models? But same here, like we want to borrow ideas, let's say from fluid, and try to apply it to other areas. Should we stop? Okay, let me stop. I mean, I understand that there is a class and we will have to stop.
We'll take one question from the audience. You for mathematical question?
Do I ask?
Yes, go ahead.
Okay, so can you relate mathematical models to the financial markets? Like, can you estimate indexes with mathematics?
To the
I
financial.
know the variance in standard deviation.
Oh, that's Martin's question. I don't know. Yeah. I mean, there are models. I mean, like that's more or less what Martin was talking about, I guess. So let me not talk in his presence about his area. Yeah, but I mean, in a sense, I mean, we can write limits. We can write limits and like, I mean, there are financial models where you can have small parameters. Let's say you take a model where you take one parameter, you think that maybe it is small, so you want to neglect it. So then the rigorous way of neglecting your parameter is to put it small and then take the limit when it goes to 0, right? So usually this kind of question usually works unless there is something where, okay, for instance here there is when there is a boundary effect, usually that kind of approximation, neglecting like the viscosity is not completely valid close to the boundary. Then you have to do something else.
Okay, thank you very much. Please join me in thanking